Welcome to part 2. In this video, I'm going to show you how to create pulse width modulation using Oscillator Sync. I learned this trick from reading the manual of the JX3P. I had a friend who was thinking about getting one, so I read the manual for fun and was really surprised when I learned about this, and a little bit jealous that I didn't intuitively figure this out on my own, because I understood how Oscillator Sync worked, but I had no idea that you could use it to create pulse width modulation. So I still have the same patch from the first video, just a regular square wave. I'm playing a B3, by the way, which is about 250 Hertz, and then despite this oscilloscope saying that's tuned to 375, it's actually tuned to 125. In other words, we're seeing two cycles, 1, 2, in the oscilloscope. So I'm going to switch over to a sawtooth wave for oscillator 2, and I'm going to go ahead and put Oscillator Sync on. What this does is it makes it so oscillator 2 is our slave oscillator to our master oscillator, oscillator 1. Every time oscillator 1 completes a cycle, it resets the phase of oscillator 2. I have a little illustration here to show you what that looks like, and I'm actually going to pop back open Cubase. Oh, you know what? If I do this, if I don't full screen it, I believe I can show you both screens at the same time. Nice. Okay. So again, just a regular sawtooth wave with sync on. Right now, both oscillators are tuned to the same number, so there's going to be really no difference in timbre for our oscillator 2. And mind you, we're only listening to oscillator 2. We're not listening to a sum of oscillator 1 and 2. So let's say that oscillator 1 is a sine wave. It's not, but let's just say that this is our master oscillator. It doesn't really matter what the master oscillator is with Oscillator Sync. It just matters how fast the master oscillator is going, because whenever the master oscillator completes a single cycle, it forcefully resets the phase of the slave oscillator. So if I turn up the pitch of oscillator 2, you can see that we get a timbral change, but also the structure of the waveform changes. You can see a full cycle, again, because this is going faster than our master, it's completing a full cycle, and then a little bit of a second cycle, which manifests as a little, kind of like a little sawtooth wave. If I were to go all the way up an octave higher, we would actually be able to complete 2 full cycles in the span of a single cycle of our master oscillator. Now, before I actually hit the octave, I'm simply changing the timbre of the slave. If you notice, the fundamental is the same. It's only the overtones that are changing. Unless I go an octave higher, then we lose that lower fundamental. Because in every case, we're only really changing the structure of this. The full waveform, or what we can consider the longest part of the waveform, is still locked to the fundamental of the master oscillator. So if I were to, instead of pitch oscillator 2 up, our slave oscillator higher, what if I were to pitch our slave oscillator lower? Well, in the first example, I want to point out that the slope of the sawtooth never changes. But in this example, if we go lower, then we're elongating the waveform, so it's a cycle takes longer to complete than our master, and thus it goes out of the range of our reset period. And so all we're effectively doing is kind of changing the slope of the sawtooth waveform, which is as ostensibly like turning it down. It just manifests as a kind of drop in volume. So that's how a sawtooth behaves. Let's look at how a pulse square wave behaves. So if I am speeding up my slave, then I will get a little bit of a square wave at the end here, but it won't be a full pulse width. It won't be like a 50-50 duty cycle. It'll just be just a narrow pulse width. So let's try that out. So you see that? Just a little narrow pulse width there. before it gets reset. And then if I, of course, go an octave higher, we will get 2 whole cycles before fitting into the span of 1 cycle of our master. And now finally, where things get interesting, is if we look at what happens when we turn down the square wave. So if I turn down the square wave, oscillator 2, our slave oscillator, the first half of the cycle will take up most of the period of 1 cycle of the master, and then the second half will actually get abruptly chopped off. And I have these little dotted lines showing you what the waveform would look like if it wasn't being forcefully reset from the master. And that is going to manifest as pulse width modulation. So noticing the oscilloscope here. Of course, if I go a whole octave lower, then this will be 1 cycle, or 1/2 of a cycle will be the entire cycle of our master, and thus we would just be creating a DC offset and get no sound. Now let's look at setting up modulation to make this behave like pulse width modulation. Minimize this. Okay. So I know that I want to change the pitch of oscillator 2 to basically modulate an octave, right? So I'll use an open LFO, in this case LFO 2, and I'm going to set its frequency down to 15 to match our frequency of LFO 1. And I want to patch it into the pitch of oscillator 2. So I'll go ahead and patch LFO 2. And then I'm actually going to set the intensity AMS to be triggered by switch 1. And I'll have the intensity at, let's have it at +6 semitones. The reason I have it at +6 semitones is, if you remember from the first video, if I modulate something with a bipolar LFO, that would be 6 semitones in both directions. But I'm actually going to turn this into a unipolar LFO. So I'm going to put it 99. So it's just going to be in the lower half of the pole. And that unipolar LFO will now be the span of 12 semitones with a setting of 6. So it's 12 semitones in one direction. It would be 6 semitones in either direction without the offset. So with this setting, I'm pretty much all set up to be modulating the pitch of oscillator 2 to create a kind of pulse width modulation. So let's actually look at that through the oscilloscope. Now here's the thing. I actually wanted to start in the same spot as I was having it start last time with just regular pulse width modulation. So right now it's starting a bit offset. So if I put the start phase on 90, then it should start the way where I want. Yep. So we're starting in the middle, and then we're doing full pulse width modulation. Now, since we're controlling this via switch 1, I can actually simply turn it off and switch back to having the pitch of oscillator 2, controlled by our LFO 1. So in other words, sorry, did I say the pitch? I meant the pulse width. So with the switch off, LFO 1 is conducting pulse width modulation, but with the switch on, we're using LFO 2 to change the pitch of oscillator 2 to create pulse width modulation using Oscillator Sync. It's pretty complicated, right? Which is why I love it. I think it's really neat. So I can actually, where's my oscilloscope? Here it is. So I can actually switch between the two pretty seamlessly by just hitting the switch. And you can see just how alike they are. But do you notice that there is a little bit of jumping? The reason for that kind of jump, you can kind of see that jump there. The reason is because using LFO1 to control pulse width, that's functioning off of a linear scale. It's just modulating it just with like a linear time scale. But with modulating the pitch, we are changing something that's on a logarithmic scale. Because an octave is a doubling in waveform. We're essentially getting smaller and smaller incremental steps the higher we go in terms of hertz value. It's not a linear scale. But I can actually go into my LFO2, and I can change the shape to about 34 to approximate the a kind of linearity in the frequency domain that will be similar to just regular time. So let's see what that looks like. It might be minus 34. We'll find out right now. Let me switch this real fast. Yep, it's minus 34. My bad. Let's try that. Whoops. Pretty close. It's much less of a jump. It's really neat. I like that a lot. Cool. So that's it for this video. Hopefully you found that pretty neat. I found it super neat. And in the third video, I'm going to show you yet another different way which we can create pulse width modulation. Thanks.